So far, we discussed the solution of the Schrödinger equation corresponding to the harmonic potential. Before, we managed to get the solution in terms of general contour Laplace type integral. This was obtained or achieved due to the fact that we managed to reduce the original Schrödinger equation, which contained quadratic and x coefficients, to a linear differential equation, meaning the differential equation with linear coefficients. And that was achieved with the following suitable ansatz. Probably you remember that the first function was simply the asymptotics of the original Schrödinger equation. There were two of them, and they differed only by the sign in the exponent. And we chose minus sign because intuitively we understood that what we expect to get in the end is their exponentially decaying function at large values, positive and negative values of complex variable y. However, it's clear that the ansatz with plus sign should also work, because we just will get slightly different equation on this phi function, but in the end we again must be able to obtain the same quantization of energy levels. And in fact, when I delivered the first lecture on the subject in front of my students, I thought the same, and I used this substitute, and I got stuck during the lecture, because it happened that the treatment of the problem is really different in a quite essential way from the previous one. And later I learned that most of my students also had problems with the second ansatz. So here came the idea to actually discuss all the details of the calculations as part of just the problem. So far, OK. Now let's see what kind of changes this sign flip brings to our equation on phi function. So here is our equation. And the original equation, so this is for the plus sign ansatz. And for minus sign ansatz, the equation was very similar, but simply with minus sign here. And the new parameter was related to the energy by the following relation. Here, however, their connection is slightly different. So 2 nu is now equal to 2e over omega plus 1. From this point, their exploration of the analytical structure of the equation is almost identical. So again, we write down p and q polynomials, which is, so the p polynomial is identical to the previous one. The q differs just by sign. And the corresponding integral becomes t squared over 4 with plus nu logarithm of t. And as a result, we get our constituent functions. The function, which is now e to yt plus t squared over 4 times t to nu z function. And the exact solution in terms of contour Laplace type integral. Right. So to get the idea of how to position the contour, again, we look at the structure of the v function and our integrand. And again, we notice the same kind of exponential function. But here we have a plus sign here. So the condition for the convergence of the integral, as well as the condition for the vanishing of v function, is the following. Real part of t squared should be now negative. And this immediately gives us the corresponding regions in a complex plane. Again, these are angled-like regions inclined by 45 degrees each. but this time they are up and down regions, not right and left as before. Now it's time to recall that we deal with multivalued functions, and somehow we should fix the regular branch of this t to new multivalued function. Before we do so, however, let's also recall that we should position our integration contour in such a way that it starts and ends in this shaded allowed region. So basically it's a vertical direction. This way, we also choose the corresponding direction of our branch cut. Since our contour is going to be positioned in a vertical manner, then our branch cut, let's choose the vertical position of our branch cut. And now we can write down two linear independent solutions. So for example, the first one can be that kind of vertical contour. So this is the one. And the second one could probably be the right contour, which is placed to the right of our branch cut. Before we draw it, however, let's actually look at the structure of our exponent function. Because the saddles of the exponent can actually define the asymptotics of our original solution. By the way, the asymptotics of our solution, so the original wave function should decay at large values of y. This imposes much stronger condition on our phi function, because it's not enough to require that phi function simply decays like power law or something. In order for the whole solution to decay at large values of y, we need to require that phi function decays faster than the exponential times minus y squared over 2. Right, so let's figure out the possible position of the saddle points. So here is the saddle point equation, and the saddle is positioned at point minus 2y. So for positive y, the saddle is somewhere here. Their steepest descent direction is defined by the argument of the second derivative, which is 1/2. So the argument is 0, and the steepest descent direction is simply pi by 2 plus pi n. So it's a vertical direction, and here we go. So we may place the contour in such a way that it passes through the saddle in the steepest descent direction. And so we see that the contour which lies to the left just may be freely deformed into the correct position. And the asymptotics of our solution will be defined entirely by this saddle. So let's compute the value of our exponential at the saddle. So f of minus 2y is equal to minus y squared. So the whole solution will behave like e to minus y squared. And multiplied by e to y squared over 2, it will give us the normal decay of our original wave function, which is good. Now let's see what's going to happen if y becomes negative. If y is negative, then our saddle will be positioned to the right of our branch cut. This way, our saddle is positioned to the right of our branch cut. And in order to get the correct asymptotics, we need to move the contour down along the relief of our exponent function, or rather its real part, the relief of the real part of the exponent function. However, when we do so, we encounter the branch point and the branch cut. So let's articulate the details. So here is again our saddle, and the steepest descent direction is again vertical. because it doesn't depend on the value or on the sign of y, actually. It doesn't depend on y at all. So the stationary phase lines are this one, the steepest descent line, and in fact, the perpendicular line, which correspond to the steepest ascent direction, ascent from the saddle. So, and this steepest ascent direction is in fact this line arrives right at the branch point. So, as we move the contour, trying to put it to make it pass through the saddle, we encounter the branch cut. And the steepest descent direction from the branch cut, obviously, is this horizontal line. So what's going to happen is that, since this is the steepest descent direction, this point lies higher on the relief of the real part of the exponent function than the saddle. And it is the branch point that gives the major contribution to our asymptotics at large and negative values of y. So what will this contribution look like? Well, it's not very difficult to figure it out, because these asymptotics will be defined by the small values of our t variable. And for small t, our exponent function is usually simplified by is reduced because it's reduced to its first term, yt. And hence, the integral can be taken. And so what's going to happen? The contour hooks up the branch cut. And the correct contour deformation is as follows. So it's positioned somewhere vertical. Then it goes along the steepest ascent direction to the branch point, circles around it, slides beneath the branch cut to the Riemann sheet below it, goes in the opposite direction, continues in the opposite direction along the steepest descent, and continues along the along the lower Riemann sheet of the complex plane of complex variable t. Okay, and we have the following integral. And there are two major contributions, from the lower branch and from the upper branch. And actually, this is a, so y is negative. So it's a gamma function type integral, because we take it from, when we slide along the lower bank of this contour, it just taken from plus infinity to 0. And then when we slide along the upper bank, it slides from 0 to plus infinity. Anyway, as you remember, that kind of gamma type function integrals always gives you 1 over y2 nu at large values of y. So there is no exponential suppression of our phi function at large negative values of y. So it should be modulus of y, of course. And that means that the original psi function, the wave function of our Schrödinger equation, will blow up during the due to the presence of the first exponential term. So due to the presence of this branch point, we got the wrong asymptotics at large and negative values of y. And things with the second linear independent solution are even worse, because, for example, if y is positive, then again we have the same story, but it's reverted from right to left, because we want our solution to be defined entirely by the value of our exponent function at the saddle. But as we try to move the second contour from right to left, so it passes through the saddle for large and positive values of y, again we encounter this branch cut, and the integral will be defined entirely by the vicinity of the branch point, and it will give us precisely the same kind of asymptotics, which leads to the wrong asymptotic behavior of the original wave function. So this is the main reason why we can't get the bounded wave function for arbitrary values of this new parameter, which is basically our energy. And the main culprit here is the branch point, or rather the branch cut. So we should get rid of the branch point. And the only way to get rid of it is to put nu to be equal to some integer value n. This integer can be positive or negative, so we'll have to basically investigate both cases. But now at least we are sure that it should be some integer number.